Welcome to this online introduction to TTCN-3. My name is Julien Deltour and I will present you what is TTCN-3 and how to use it. TTCN-3 is an acronym for Testing and Test Control Notation version 3. This is a test-specific language standardized by the ITU and developed and maintained by the HC. The TTCN-3 was firstly used in the telecommunication, but is now well deployed in other domains such as transportation or financial application. TTCN-3 is a high-level language and is totally platform independent. TTCN-3 test scenarios are specifically made for black box testing. It can be used for several types of tests as validation, unit, functional, or regression testing. I will now explain how is TTCN-3 structured. In TTCN-3, the module is a top-level container. All code must be written inside a module. The main goal of the module is to organize and structure the code. A module contains a declaration and an optional control part. It is easily possible to import a module in other brand or just import a part called a group. As shown in this example, to define a module, the keyword module is used, followed by a unique name. All the TTCN-3 code has to be written between the curly brackets. TTCN-3 provides data types available in other classical programming languages. There are basic types, such as integer or boolean. There are also some complex types, like record, which is equivalent to the structure types in C, or a set of list types. ASN.1 for Abstract Syntax Notation 1 can be directly imported in TTCN-3. It is also possible to use a specific test type, the verdict type. This one is required to get the result of a test execution. The component is the execution entity of TTCN-3. The test scenarios are always executed on one or more components. Components have to communicate with other components or with the system under test, called SUT. This communication is done via ports. In this example, a component type named access control is declared with one port named C-on. This component can be seen as a box with one port as interface. As seen in the slide before, components need to communicate. The ports are the interface of a component. It is through these ports that messages are sent and received. Ports are based on a FIFO mechanism. Each port has to be mapped or connected to another to drive the communication. This example shows the declaration of a new port. 2 messages can be sent through this port, card and key, and 3 can be received. The port type will then be used for a component declaration to define its interface. The test system interface, called TSI, is the interface between the test and the SUT. The TSI is just a component with port, nothing is executable inside. All communication between the test and the system under test will be done through the port of the TSI. A mapping has to be done between the different components of the test and the TSI. The test case is a behavior description of the test. A test case will simulate the system and then will check the answer to this stimulus. Architecturally, a test case is composed of one or several components, with a test scenario executing on each one and a TSI. The test cases are started in the control part by using the keyword execute, with the name of the test case to start. By doing this, 2 components are created, one for the TSI and the other one for the execution of the test case, the MTC, for main test component. Here is an architecture example for a simple test case with only one component. As said before, this component is the main test component. There is also the TSI, which plays the roles of interface between the MTC and our system under test. If nothing is specified, the TSI is built on the same component as the MTC, meaning that the two have the same port. In that case, an implicit mapping is done between the equivalent ports of our two components. TTCN-3 supports the concept of function. As in other languages, functions allow to easily reuse code. There are two types of function in TTCN-3. The first one is a pure calculus function. The second one is a communication function to express test behavior. This type of function is used in case of multi-component test case. As said before, a test case can be composed of one or several components. In the case of a multi-component test case, there is one NTC and all other components are called PTC for parallel test component. The behavior of a PTC is described in a function. When a multi-component test case is started, only the MTC is started, and it is the MTC which will start all the PTCs. This example shows the creation of a PTC by the use of the create operation. Then we start the execution of this component by calling the start operation with the function we want to execute as a parameter. This example shows the architectural representation of a multi-component test case. There is one MTC and this one creates two PTCs. In this case, a mapping must be done between the different ports of our component. The keyword connect is used to connect two internal component ports. The keyword map is used to connect an internal component port with the TSI. TTCN-3 allows two types of communication: synchronous, based on procedural call, or asynchronous, based on message exchanges. The type of communication is specified during the port type declaration. A port declared as message-based will only be able to send and receive messages. Messages are declared in the TTCN-3 as a record, with a field for each parameter of the message. For example, a message with two parameters, one integer and one char string, will be declared as a record with two fields, param1 of type integer and param2 of type char string. A template defines one or more values of a specific type. Templates are used to easily send messages or to check the value of received messages. In this example, a new record type named displayMessage is declared with a char string as field. Then, a template based on this new type is declared with its field set as EnterCard. This template can now be used to easily send the message displayMessage with its parameters at EnterCard, but can also be used to check a message reception and the value of its parameter. Message-based communication has two main operations. The send allows to send a message via a specified port. The receive operation waits for the reception of a message and checks the type of the value of this message. It is a blocking operation, meaning the test will stop until a message has been received. The receive operation removes the top message from the port queue only if it satisfies the matching criteria. If not, the test case will fail. Here is a send of message request 1 through the port P1. The second action waits for the reception of the message answer 1 and checks the value of its parameters. As seen before, the test case is the behavior of the MTC. In this example, a new test case named Testcase1 is defined. The keyword runs on indicates on which component type the test case will be executed. A test case is a sequence of send and receive operations. The send will stimulate the SUT, and then the test case will wait for an answer with the receive operation. If the received message does not match with the waiting one, the test case fails. But what if many message receptions are possible after a send operation? Alternatives are useful in the case where several exclusive alternatives can be possible during a test case. An alternative branch can be evaluated on a variable value or on a message reception. In this example, two alternatives are possible. If the test receives the correct answer, then action 1 is executed. Else, if other answer is received, then action 2 is executed. All the branches of an alternative have to be evaluated with the same information. A snapshot is a save of every relevant information of the test case. If anything occurs during an alternative, for example, a new message in a port queue, This event will not be used for the evaluation. If no branch is favorably evaluated, a new snapshot is taken and all branches are re-evaluated. Alt step can be seen as a function, but only for alternative. An alt step can be activated at the start of a test case, and the branch defined in this alt step will be added to all alternative statements in the test case. In this example, if the alt step fail alt is activated, a new branch testing the reception of the message wrong message will be added. The verdict is the result of the test case execution. 5 values are possible: none, pass, enconc, fail, and error. The set verdict operation allows to modify the verdict value of a component. Error verdict is special because it's set by the system itself, when, for example, a runtime error occurs. So it cannot be set by the set verdict operation. Get verdict operation returns the value of the current verdict. The global verdict of a test case is the worst verdict of all its components. I will now make a demonstration with a TTCN-3 complete test and will confront it to a simple system.
To do this example, I will use Real-Time Developer Studio, a modeling and testing tool. Let's open the project for the example. This project is composed of 2 parts. The first one is the test file, the second one is the system under test. First, I will open the SUT. The system to test is composed of only one process named P1. This process can receive the request message and send answer message. These 2 messages have been declared above. Request is a message with 2 parameters, the first one of type myNewType, which is a restricted integer, and the second is a charstring. Answer message has 1 parameter of type myNewType. Let's now open the process P1 and see what it does. Process behavior is described as a state machine in SDL. Process starts and goes in idle state, then reads the message queue and waits for request message. It will then check the values of its parameters. If the first one is equal to 42 and the second one equal to hello, then the system will send back answer with the value 0. In any other case, it will send back answer with 1. The goal of the test case will be to check the good behavior of this system. I will now write the test. Let's open the TTCN-3 file, here called test system. The first thing to do is to declare the module. I will also name it test system. As for the system, I will declare a new type, an integer restricted between 0 and 15. Now the messages. As seen in the system, there are 2 messages, request with 2 parameters and answer with 1. In TTCN, a message is declared as a record. So let's start with request. I will declare a field for each parameter, the first one of type myNewType, the second one of type charstring. I will do the same thing for answer message and its parameter of type myNewType. The next step is to declare the port, which means the interface between the test and the system. Here I will name my port type CONF-type. Because the system can receive request and send answer, the test will have to send request, I set it as an output message, and will receive answer that I set as an input message. Now that I have declared the port, I will declare the component on which the test case will be executed. This component type will be called sSystem, and I declared it with 1 port of the type CONF-type. Remember that the goal of this test is to check that if I send request message with 42 and hello to the system, it must send me back answer with the value 0. To do that, I will declare 2 templates. The first one, that I call GoodRec, is based on request record. This one will be used to send the message request with the values 42 and hello. The second one is based on answer record and named all is OK. It will allow the test to check that the parameter of answer is equal to 0, so I set its field value to 0. I will now write the test cases, which is the behavior of the test. I call it test case 1 and tell it will run on a component of type SSystem. The first thing the test will do is to send the request message with the good parameters. To do so, we write the port name, here CERV, followed by the send operation with the template GoodRec as parameter. Now, two cases are possible. The system can send back answer with the value 0 or the value 1. For handling these two cases, I will write an alternative statement. The first branch is triggered by the reception of the message answer with the value 0. To do so, I use the receive operation with the template all is OK. This behavior is what I wait for my system, so I set the verdict to pass. The second branch of the alternative is triggered if the message answer is received with 1. I could have written another template based on answer, but with its field set to 1. But here I just write receive with no parameter, meaning anything else that's the trigger of the first branch. In that case, it's an error, so I set the verdict to fail. Now I end my alternative statement and my test case. I finish with the control part where the test case will be started. I declare a verdict type value to get the verdict of the test case. And I ask to the control part to start my test case by using the operation execute. Now my test case is ready, so I save it and close the file. I will now run the test against the system to test. To do so, I select my test file and start the execution. In the simulator window, I start an execution trace to conserve an history of the execution. And then I start my simulation step by step. The control part starts and creates verdict 1 value and executes the test case. The first thing the test case does is to send the message request with the good parameters, and then it enters in the alternative statements and waits for an answer. Now the system under test starts and receives the message sent by the test. Then it sends back its answer. The test receives the message and the first branch of the alternative is triggered because the parameters are correct, and the verdict is set to pass.
Thanks for your attention. You can find more information on TTCN3.org website or on our website PragmaDev.com.